So today we have Andrew speaking on enumeration of Forman equivalence classes.
All right, hi guys. So I'm Andrew Tawfeek. What is it? I'm an undergraduate, a senior at Amherst College, and yeah, I'm going to present on enumeration of Forman equivalence classes. So Forman equivalence classes are an equivalence class of discrete Morse functions. So we'll be just doing kind of a brief overview of discrete Morse theory, and then getting onto how they've been, how we were able to count them and future directions. Yeah, so hopefully it goes well. All right, so a quick overview of discrete Morse theory, I suppose, before we jump right in. So, what is it? Okay, I'll mention, I guess, this out loud and won't have to necessarily write this part down, but smooth Morse theory came much before discrete Morse theory, and through studying Morse functions. So let's see. So here's, I guess, background. So in smooth Morse theory, you studied Morse functions, which were, so let's see, a Morse function is a smooth, non-degenerate, function on a manifold, on a smooth compact manifold. And through studying the properties like critical points and such of this function, you were able to understand a lot of the topological properties of the manifold in question. So we're gonna, I'll showcase some of the similarities between discrete and smooth Morse theory a bit later on, but some things you were able to get back were like the Betti numbers and the Euler characteristic and so on. So discrete Morse theory came along in, discrete Morse theory came around 1998, I believe, by the work of Forman, where he really wanted to replicate what happened in smooth Morse theory with Morse functions and all, and do it in a more discrete case. What is it? A CW complex case. That's a bit messy, so I'm going to actually talk about simplicial complexes instead, but a lot of what I say can be immediately generalized. The counting we did for simplicial complexes, well, one-dimensional, and I'll talk about n-dimensional later on. And it'd be interesting to see if this stuff could be done for CW complexes, because it would be kind of just all over in a sense. But anyhow, all right, so that's enough of the background for now. So let me start actually introducing concepts. So before we can talk about the equivalence classes, we need to actually define what the discrete Morse functions are. So discrete Morse functions. So let's see. So let Kc denote the cells of a finite simplicial complex K. A discrete Morse function. So a discrete Morse function f that goes from the cells to the real numbers. Discrete Morse function is, I'm sorry. Function is a map that goes from here to there, such that for any cell, tau, we need to satisfy these two properties. And these two properties are going to look a bit messy at first, but they'll become more intuitive as time goes on. So we have that at most one coface of tau has value less than or equal to tau, or equal to tau, and at most one face of tau has value greater than or equal to tau, or equal to tau. If my handwriting ever gets also too messy in any way, or something's unreadable or something's unclear, feel free to stop me, and you can full on just interrupt me. So this definition looks a bit messy, so let's immediately, oh no, I don't want to spoil that. Let's immediately just look at an example. So here is an example on a two-dimensional complex. So this is what I mean by values. So if you look at, for instance, let's say this cell here, this one-dimensional cell, it has the assignment of 20. And if you look at the lower dimensional cells, well, if we look at the higher dimensional cells, which might be a bit easier, what is it? Okay, well, let's look at this one. 20 is not as interesting. So at most, one of the lower dimensional cells has higher value than the two-dimensional cell labeled 18. And if we look at any of these edges, we see that at most one of their endpoints can have higher value. So in this case, there's -2. In this one, they're both less than, which is something special, which I should actually define before I talk anymore. So if you look at, for instance, the cell right here, you'll find that in a sense, it's kind of a local maximum. So we have this definition. We call a cell sigma in KC critical under a particular Morse function. So I'll just say under F if locally the assignments increase with cell dimension. I know that's a bit vague. Well, the more precise way to say this is if you consider both of these things as sets. So the sets of, like the first one would be the set of things, the set of cofaces that have value less than or equal to tau, then you want both of these sets to have zero cardinality. And in which case you would say that that cell that you're looking at is a critical cell. So in this case, we can look at, for instance, this vertex here, and you'll find that, for instance, my mistake, sorry, double checking work because I got a bit worried that something was off. I don't think something's off, but yeah, so basically if locally the cells increase with dimension. I don't know if I'm mistaken, but I almost thought there was a mistake in that one, but it seems like it's a discrete Morse function. So feel free to stop me if you spot an error with the according definition. I don't think there is one, but anyhow. But yeah, so basically if locally around it, so in the case of an edge, both of these would have to be less than the edge, and that is precisely what happens in at least that one. So this edge right here would be considered a critical edge, and in a sense, a local maximum where it is. So let's see. For any complex K, there always exists a discrete Morse function. So there exists a discrete Morse function. So this is kind of the trivial one that exists for any complex, and it's just by sending all the cells to their dimension. And all cells, you might notice, are actually critical under this assignment. So according to what we said earlier with cells increasing by dimension, well, this is the most literal way to translate that. Okay, so similarities between smooth and Morse, smooth and discrete. So far it looks like this definition that Forman came up with kind of came out of nowhere. It's a bit messy. I personally don't really like it. But let me start showing some of the similarities between smooth and discrete Morse theory, just so you can see that this is almost kind of a natural way to define things. So here's smooth on this side, and here will be discrete. So on the left side, I'll just start, I'll put some things that come from smooth Morse theory, some theorems and whatnot, and I'll show you their analog in discrete Morse theory. So what is it? If f that goes from M to R is a Morse function on a smooth compact manifold, what is it? So let Ci denote the number of critical points of index I, then we have, this one is called the weak Morse inequality. where this thing right here is the Betty number. And we also have the strong Morse inequalities, which state this. And where on the left we have the Euler characteristic of the manifold. The second thing is actually equivalent to a differently phrased statement that has to do with the Morse complex, which is this chain complex that has a particular boundary operator that comes from Morse theory. But I won't say it that way just because it's a bit unrelated to what we're going to be discussing. But yeah, so the second statement can also be written in a different way. So in the discrete case, let f from k to r be a discrete Morse function on a simplicial complex K. Now let Ci denote the number of critical cells of dimension I. Then we have exactly the same statements. I equals 0 to n. Oh, sorry, where n is the dimension of the complex and manifold, respectively. Yeah, so far seems really similar. And if I'm ever scrolling too fast, feel free to tell me to slow down as well. Let's see, I'll mention one more thing, and then I'll give you kind of the connection between the two. So sublevels. So let's see. So one common thing that people learn in smooth Morse theory has an analog here. So let's see. So again, let f be a Morse function on the manifold. So if A is in R, define the sublevel set. M sub A. I'm just going to move this a bit to the left. To be all the points in the manifold such that the value they got assigned under the Morse function is less than A, or less than or equal to A. Then there's this theorem that says if f has no critical values in the interval AB of R, then MA is a deformation or retract. Deformation, retract of MB. This has a complete analog in discrete case. So f again, going from k to r is a discrete Morse function on a n-dimensional simplicial complex. So if A is in R, the level subcomplex K of A is the subcomplex consisting, subcomplex of K consisting of, is the complex defined. Let's see, what's the best way to write this? Maybe this is the best way. Consisting of all simplices tau with f of tau is less than or equal to A, but we still want this thing to be a simplicial complex, so we need this extra condition. And I'll what is it? And I think it's all subsets of tau. Subcomplex consisting of simplices of tau. Let's see, what's a clean way to write that? Okay, maybe this, okay, yeah, let's just write it a different way instead. But so yeah, we have all the simplices with f of tau less than or equal to A. But I'll just give you a compact definition that seems a bit easier than writing it out in words. So we have this, and then we have, oh dear. I have a good feeling chalkboard would have actually been easier. So there we go. So you have, what is it? It's the union of all the simplices that have this condition, which is similar to what we have over here on the left side, but we also need that extra condition that we also want all the things that are contained within those in order for it to actually still be a simplicial complex. And here's the theorem. So this is the theorem on this side. Here's the theorem on this side. If f has no critical values in the interval AB subset of R, then KB collapses to K of A. So let me quickly do a demonstration of what that means. So this means you just collapse, what is it? Simplices. And if you haven't seen that before, here is an example. Let's see. So I will quickly, thankfully I wrote these numbers down beforehand. So let's let this thing on the inside be a two-dimensional complex. And the numbers are going to be 12, 5, 11, 10, 9, 8, 4, 3, 9. So I'll just point them out to you. Oh, this bottom one is a 3, by the way. The two critical cells in this one are these two, this edge and this vertex. And those can easily be checked with the definitions, but we'll quickly go over an easier way to spot them out rather than relying on that very kind of clunky definition. We have K12, which is just K. Collapses to, 10. And 10 looks like this, where the two-dimensional simplex has been collapsed. Let's see. So I won't write this next statement just because it's a bit long, but I can just say it out loud. So Forman also proved that a lot of discrete Morse theory actually just implies the corresponding smooth theory. And if someone wants me to write this down, I can. Here, but I'll just write this one statement. So Forman showed in 1999 that discrete Morse theory implies the corresponding smooth Morse theory. The corresponding smooth Morse theory. In fact, the exact theorem statement that he proved was if M is a smooth manifold with a Morse function, then there is a C1 triangulation of M in a discrete Morse function on the resulting simplicial complex, which has the same Morse data as the original function. So meaning like the number of critical points is preserved, they have isomorphic Morse chain complexes, and Morse chain complex is the thing that I purposely didn't define, but basically the Euler characteristic material is preserved. But yeah, so in a way, discrete Morse theory gives you back smooth Morse theory. Now there are some theorems, I don't think I will mention any of them, but there are some, of course, differences between the two. But yeah, so discrete Morse theory does kind of give you back smooth Morse theory. Okay, so now I feel like that's a good background. People hopefully have kind of a good idea of how the two are related to one another. So let's actually get to the stuff I want to discuss. So gradients and classes. All right, so personally, I very much dislike the numbers on the graphs and the complexes. I don't like numbers, so I prefer this a lot more, and this will help really kind of spotting out criticals immediately. So, but it's going to rely on this one key thing that is not hard at all to show, and you can just use the definition to show this immediately. So for a discrete Morse function f, it can be shown that exactly one of the following is true. That exactly one of the following is true. So either there exists a unique is true for okay, so maybe there's a bit more of the sentence. Exactly one of the following is true for any non-critical face sigma of dimension k. Okay, there we go. That's the actual statement. So if you just fix a sigma that's not critical, you can either show that k plus there exists a unique k+1 face containing sigma with f of tau less than f of sigma, or exactly the opposite. There exists a unique k-1 face tau containing sigma with f of tau greater than f of sigma. So this causes something special. So hence we can partition the non-critical faces into pairs sigma comma tau, where sigma is the maximal face, is a maximal face of tau and f of tau less than f of sigma. F of sigma. All right. So this is the nice thing is we can use this to kind of put a gradient or like start putting arrows on the simple shield complex and make things a lot more visual and not have to rely as much on the numbers. And this can actually be shown to be a full-on just equivalence class. So yeah, you can start talking about, oh, these two functions have the same gradient and whatnot. And we'll quickly see how this is related to the classes, which the Forman classes, which are also an equivalence class. So I really wonder what the relation is. Might actually be completely clear, but yeah, so here is, for instance, one gradient. So let's cut that and let's paste it here eventually. Okay. So here is this example. And it's really intuitive if you at least look at the graphs, the underlying graphs, because it just drifts towards the lower value. Lower value. So if you look at these values here, you can see we're just moving along until we hit essentially the rock bottom. And every now and then you'll get to an edge like this one, where going this way you're going down and going this way you're going down. And unsurprisingly, this edge right here, the one labeled 5, is critical because it's a local maximum there. And this vertex over here is a critical vertex because it's a sink there. It's a local minimum. And then there's, perhaps the intuition doesn't go as far when you're talking about a higher dimensional simple shield complex. But yeah, if you're talking about graphs, you just have basically local minimum and local maximums. All right, so how does this tie into Forman equivalence relations? Forman equivalence. So, well, two discrete Morse functions fg are Forman equivalent if and only if, okay, so I guess, yeah, all right, so I'll give you actually the definition of Forman equivalence classes and not just say, oh yeah, they're equivalent to this thing. If for every pair of simplices, sigma, and I'll just use this parentheses notation to denote the dimension of the cell. So for every pair of simplices, okay, we have f of sigma is less than f of tau if and only if g of sigma is less than g of tau. You might be able to kind of already see how this relates to the gradient notion. So this is a theorem proved by Ayala in 2009. That, what is it? F and G, so if f and g are discrete Morse functions, C are discrete Morse functions on a possibly infinite simple shield complex K, and then f and g are Forman equivalent if and only if f and g are Forman equivalent if and only if Really quickly, if this is a complex K, I'm going to denote this by K sub F, where F is essentially this function, this discrete Morse function on it, just to make things a bit kind of cleaner and shorter. So F and G are Forman equivalent if and only if KF is equal to KG. So essentially, the gradients are the same, which is nice because I personally also don't like the Forman equivalence class definition. It's a bit too local, where this is kind of feels to be kind of a cleaner way of looking at the entire picture. So the question I kind of asked and was curious about is how many gradients are there, or at least on a finite complex. I don't know the answer for infinite complexes. That is also one of like the questions as someone pursuing kind of that direction. But I was curious just about like on finite complexes that are kind of simple and neat and easy to think about. So jumping right into the n-dimensional ones seemed particularly hard. So the easiest thing to do was to, of course, start at one dimension and start at graphs. And the answer was pretty interesting, I'd argue. So quick note that unless otherwise noted, when I say gamma, so gamma is a finite, simple, and connected graph. And I'll show you how the one-dimensional case is enumerated and how higher dimensional cases may be enumerated. All right. So let's also kind of give a name to exactly what we're counting. So I'll give you something that at first kind of, it's gonna seem a bit weird that I'm defining this one, but yeah, this is a fancy M. Let's see. So this is gonna be the set of gradients on gamma having k many critical edges. Critical edges. So it's a bit weird that for some reason now I'm kind of focusing on the number of critical edges, but it'll make a lot of sense kind of soon. And M gamma will be all the gradients on gamma. And by what Ayala mentioned earlier, this is, what is it? So this is going to be equivalent. So this set is the set of Forman equivalence classes. And notice just because all these M sub Ks are disjoint, we can just say, we'll let J go from B1, oops, not BI, B1 of gamma to the number of edges of gamma. So we can just take the union of them all. And just because I mentioned it in passing, didn't talk about it too much, the reason we're starting at B1 is due to one of the Morse inequalities. So here, I'm gonna just scroll up just so no one misses out from this one right here. So the number of critical cells has to be at least, the number of critical edges has to be at least the number of essentially holes in your graph. And we'll actually be using this one and this one moving forward. So just a quick heads up. But yes, so that's why we have that. We're just starting at B1, and otherwise they're, I guess, 0 or T. But yeah. So let's see. Also, we'll call gamma F a Morse pair instead of repeatedly saying let F be a discrete Morse function on a graph gamma. I'm just gonna say for short. But yeah, so just to not keep having to say the whole thing, and frequently like the graph might change, the function might change. So it's just easier if there's this short notation where we can keep referring to them easily. But yeah, for short, yeah. All right. Okay, so now let's kind of get into some of, so this is kind of the very, very, very basic results. These take no more than a line or two to prove, but they are kind of necessary for understanding things. And I'm sure some of you guys, even if like you haven't seen this subject before, might actually be able to beat me to the punch by just because like the more of these propositions I give you, the clearer it's going to become where we're kind of headed with what exactly are these counting. All right, so let gamma f be a Morse pair? Be a Morse pair. So maybe some of you noticed this already. Well, actually, I think I said it already. Let's see. So an edge E is critical if and only if E is undirected in gammas in the gradient. So if we scroll back here, you can see this edge that we were talking about earlier is indeed undirected if we look over here. And the second one, a vertex V is critical if and only if V is a sinc. And again, if we go back up, here we can just follow these edges over here, and yeah, that one is indeed critical. And is this one? No, this one is not critical. Okay. But yeah. So let's see. So that's one thing. Here is kind of another helpful little gadget. So if n is greater than or equal to 3, and Cn f is a Morse pair, say Morse pair. So where Cn is the cycle graph with n vertices. So then the number of, so this notation was used in the Morse inequalities. Then the number of critical edges, the number of one-dimensional critical cells, is greater than or equal to 1. And this can be also proved very quickly. Here's C4. Well, I mean, if you started, so the way you would go about doing this is you would say, okay, so let's consider some random, discrete Morse function on it. Let's look at this gradient immediately. And let's just say the gradient was kind of spinning around. Well, that's going to be a problem because that would essentially be saying that, if this was perhaps the number 0 at this vertex, this edge right here, according to the definition, would have to have a higher value than it. So we'll let that be 1. And this vertex can also be 1. That's completely fine. And this one could be 2, 2, 3, 3, 4, 4, and you get this kind of contradiction. And then there's a similar problem if, you ever try to have 2 edges leaving a vertex, this vertex becomes a problem and it breaks the definition. So just using that, you get that there has to be a critical edge on every single cycle. And yeah, so that's an important kind of, I guess I'll just write it like this. What is it? So so this is just using same notation as the one above. Every cycle Z and gamma has a critical edge on its boundary. By boundary, I mean the edge set of the cycle. Because what is it? I didn't mention this. I don't think I need to necessarily show it in detail because I feel like it'd be very clear. But if you have a graph or even just a simple complex in general, then of course if you like just associate the numbers with the cells just because it's easier that way, and then you delete some part of the complex, that remaining assignment on the subcomplex is a discrete Morse function on that subcomplex. So that's essentially what we do in this case. We have a graph that has cycles, we restrict to a cycle, and by that previous lemma, it means that cycle needs a critical edge. But what does that mean then if you start deleting things? If you delete critical cells, remain, okay. Don't know why I'm forgetting English this morning. Okay, so we have just one last thing we need to mention before we can start counting the classes. So we're going to define this little gadget. So if gamma f is a Morse pair and x subset of the edges is the set of critical edges under f, let our gamma f be defined to be the edge subgraph. Sorry for taking such a combinatorics turn at a topology thing. The edge set of the gradient minus x. Within, technically I should write this, gamma of f. So in other words, what is it? So the edge subgraph is, so this thing right here. So what an edge subgraph is if you have some graph and you take some set S, subset of the edges of your graph, then the edge subgraph is is the graph that consists of those edges and the vertices incident to those edges within the original graph. Yeah, so I'll draw an example quickly of remainders, or actually I'll copy it in because I was too lazy to try it, but it should make it a bit easier in a moment. Actually, I'll just do it now before proceeding, and you'll probably guess what the next theorem I was about to write was. So here is, oh no, is it gonna fit? Okay, there we go. Okay, so here, for instance, are all the remainders, all the different critical configurations on the graph W4, the wheel graph. And technically, this isn't quite right because I said this is a subset of the gradient. So actually, each one of these represents 4 different graphs. And the 4 different graphs it represents are the 4 different ways you can essentially choose a root of the tree. So here's one way, here's another. Then we can go to this one over here. And then lastly, lastly, we can go to this one by just going like that. And I imagine it's probably clear that I am about to write this, that R of gamma F, where C1 of F, so the number of critical edges is equal to V1. Well, this is actually just a set of rooted spanning trees. Rooted spanning trees of gamma. And yeah, so that's kind of the first little mini cool result. So my hope is by this point, like this, that I've hopefully given you enough where this almost feels like obvious by just like looking at this. Of course, you know, all cycles can't have critical edges and so on. But yeah, so in this case, these are actually all the, you know, spanning trees. Let's see. So for the proof, I mean, okay, I'll put the smallest possible sketch of this proof. It's really, there's no kind of, you're just kind of definition chasing to get this. Let's see. So I believe you'll trust me that I say R gamma of F has no cycles. And so for any discrete Morse function, and it's an edge subgraph on, what is it? So if it's on V, so like the number of vertices of the original graph, V minus 1 edges, then it's a spanning tree of the graph, given it's given it has no cycles, and we just wrote down that it has no cycles. And as for the number of edges, well, if you just do it really quickly, and at one stage you'll have to use the strong Morse inequality. So really quickly, you have gamma F. This is just minus X. This is just the Betty number. And just the definitions of things. You have gamma F plus, oh dear, B0. Okay, that's B0 of gamma F. And this is just going to equal V gamma F minus B0. And because I said at the start, all the graphs are just assumed to be connected, that's just equal to 1. So it is indeed a spanning tree on this many edges. And for the other way, we just construct the function. So this is actually not very hard. I think I've mentioned it in passing. So here I'm going to really quickly draw a fairly simple looking graph, but I just wanted it to have kind of enough cycles where it's clear how things are happening. So So imagine this, ignore that the edges are red, but imagine this is just a random graph and I gave you a spanning tree, sorry, a rooted spanning tree. So here's a rooted spanning tree and having them all chase this root here. And then all we'd want to do is essentially number this, what is it? We'd want to assign values to each of these cells such that it produces this gradient. And that's actually almost kind of silly how I'm gonna go about this. But so let's start at the root right here, and I will assign it the value 0. And then since the values go up along the edges, you can probably imagine exactly what I'm gonna do. I am lazy, so I'm just gonna, oh, when you get to a critical edge, you want it to be a local maximum. So you just take the maximum of the two endpoints and just add 1. So here's 5. So, and yeah, and yes, 3, 4, 5, 6, 5, 6. This one can be 5. I think I did that right. And yeah, so someone can of course check that that indeed is the gradient of that function. We just scroll down. So yeah, I'll leave that there while I quickly scroll here. All right, so now let's actually get to the counting. So corollary of that above thing is through Kirchhoff's theorem, and it basically says that m of b1, don't know why my handwriting is noticeably getting much bigger as the talk goes on. Let's see, so m of b1 of gamma. So this is the number of gradients or number of Forman equivalence classes with b1 many critical edges. So that is the least amount of critical edges. This is actually just equal to gamma 1 times dot 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 gamma n. So I'm gonna start scrolling down now. Where gamma I, where the gamma I are the non-zero eigenvalues of the graph Laplacian. And to get this, you just, oh no. To get this, you just apply Kirchhoff's theorem. I'm gonna keep going. I'm kind of, okay, battery's kind of far. All right, hopefully, you know, all right. So you apply Kirchhoff's theorem. If you recall, Kirchhoff's theorem actually has a 1 over the number of vertices up front. But the reason that you get rid of that over here is because you're looking at rooted spanning trees. So for every spanning tree, you like count the vertices. So essentially that factor just cancels out. So, all right, so we have this. And well, there's still kind of the question of, all right, well, what about the rest? I mean, and let's quickly go off and do that. So let gamma f be a Morse pair. And now let's just consider a more general case where C1 of f is equal to the Betti number of that graph plus k, where 0 is equal to k. Less than, I told you not to do that. E minus b1. And now by the strong Morse inequalities, by the strong, well, Morse inequality, strong Morse inequality. What is it? We have this. So I imagine this is probably at the point where most of you already see what I'm doing, and I'm just wasting time. Our gamma f plus C1 of f. So this is just restricting plus B1 of R of gamma f. And this is all equal to C0. So I'm just saying the number of connected components of the remainder in this case is just going to be the number of sinks in the remainder. But importantly, notice that this can generally be less than or equal to the original number of sinks. And as an example, so here is a wheel graph. I'm gonna copy it, or no, I'm not gonna copy it actually. So I will draw you a quick gradient, and many of you probably already see why some critical vertices just end up disappearing. Hopefully it's clear which edges and vertices I'm trying to make critical. And then here are the non-critical things. I made lots of critical. It's easier this way. Oh dear. Okay, so maybe this was a kind of a tough graph. Okay, there. I think that's everything. And in this case, we see that C0 of f is equal to 3. Here are the 3 critical vertices. And now if we look at the remainder, well, the remainder is just going to be 1, 2, and it's going to be these. So yeah, C0 of f restricted to the remainder, in this case, is 2, and that is indeed the number of connected components. And by now, it's probably clear that, what is it, through methods similar to before. Oh, I got closer. Maybe that's why my writing is getting bigger. But let's see. So yeah, by methods considering before that, we as we were doing with like the spanning tree case, we can essentially find that, so in general, R gamma F is a rooted forest. They spell, yeah, a rooted forest. And similarly also to before, for if you give me any rooted forest, what is it? It's easy to construct the function that gives you that back. So this is where we come to a close for the one-dimensional case, where we apply this helpful theorem from Norman Biggs's book on algebraic graph theory. So this is somewhat well known. The coefficients Qi of the characteristic polynomial determinant minus lambda I, where this thing right here is the graph Laplacian. I'm just gonna write this part out because it might not be what you expect. -1 I q sub I lambda n minus I. Oh, here, sorry, I actually didn't mention it. So the number of edges is equal to n. Are given by, oddly convenient, that what I'm about to write. So f in sigma sub I, or omega, yeah. V of f, number of vertices, for 1 is less than or equal to I, less than or equal to n, where sigma I, omega I consists of all edge subgraphs of gamma, which have I edges, and are forests, which have I edges and are forests. So it's probably very, but note that the term, yeah, so what is it? But note that this right here is essentially just counting the number of different ways you can root that forest. So basically, by counting every, by counting every vertex, you're counting every single vertex you can choose as a root. So this leads to the following result. My goodness. Consider a graph gamma. Well, okay, we've been considering the entire time a graph gamma. So let V equal N and E equal M. Then the determinant of delta minus lambda I, so basically the characteristic polynomial, has this very convenient form. -1 to the I. Whoops, that is horrible. That's not much better. I'm gonna give up on that. Oh no. All right, gonna shift this very slightly. Lambda n minus 1. Minus I lied. But yeah, all right, so it turns out that the gradients were actually just counting the coefficients of the graph Laplacian. Did I expect that? When I first looked at gradients? Of course not. But it is convenient. It's quite nice. Hence, maybe this is a bit silly to bother writing, but since I technically said we wanted to count the Forman classes, and I and that's this thing right here. So this is actually just equal to the determinant by plugging in -1 to deal with that thing. But yeah, so that's the number of classes. Let's see, how are we on time? Oh, okay, we're bad on time. Okay, so, all right, I won't mention other things, but I will mention, I guess, this one example just because it's convenient. And well, this is one that's kind of worked out. I won't mention the Morse complex, sadly, but here's the case for C4. So that's this graph here. So here we have its Laplacian, here we have the characteristic polynomial, and here we have all the possible gradients. And you can see that this right here corresponds to that one gradient. The 8 is right there, 20, 16, so on. Let's see, what else did I want to, I guess, mention? Okay, that one more example, that doesn't matter. More simplicial complex. I really, it's okay. All right, so I won't mention the Morse complex, sadly, unless someone asks. But it does lead to this last result. I'm gonna skip, sadly, a lot. So if F is a forest graph, then the coefficients of the characteristic polynomial of the Hasse diagram of the forest, it's a bit weird, are in correspondence with the coefficients of the graph Laplacians, yeah, characteristic polynomial. And to get that, we talk about matchings and things. So there's this thing in discrete Morse theory called the Morse simplicial complex. So this is different from the Morse chain complex. And it's, what is it? It's p cells are given by acyclic p matchings on the Hasse diagram of the simplicial complex. And there's a very interesting connection. And it turns out essentially what we did here, that turns out these things, all the m sub k's, they actually are counting the different dimensional cells of that simplicial complex. And it would have been more fitting to start there because people care about the topological properties of the Morse simplicial complex, and like its homotopy type and stuff like that are things that are really sought after and not well understood by any means. And it tells you a lot of stuff about your original simplicial complex. And I think it's only been studied for the case where you have discrete Morse functions on a simplicial complex originally, not on a CW complex. But yeah, so that's a whole other thing. And yeah, so I guess what is it? So there's a bunch of questions to end this off on, like for instance, infinite graphs and expanding to higher simplicial complexes and such, so on. And I guess for the future directions, what I am currently working on this is it turns out that it seems very, very, very likely that this can all be, at least this statement right here, can be expanded upon into a general simplicial complex, because there is a notion of a rooted forest for a general simplicial complex. And there is also a connection between a directed rooted forest in higher dimensions and the higher combinatorial Laplacians that come from the chain complex and whatnot. So it seems very, very, very likely that all of this can be expanded. But of course, it gets much, much messier when you go higher up, because, well, now you have multiple Laplacians to deal with. Which ones are telling you what? And yeah, so things aren't going to be as pretty. Gradients are not going to be as easy to really think about anymore. You'll have to really rely on on other things. But yeah, so I guess I'll just talk there because I've talked fair enough.
Thank you, Andrew. Are there any questions?
Andrew, so to me it seems like given one of these discrete Morse functions, I get a bunch of like simplicial cocycles, because the Morse function is just describing, like how do I assign numbers to like things in my simplicial complex. So I wonder, like, is it often that I get like, sorry, I mean, coach, like, is it often that I get something that actually represents a cohomology class?
I haven't admittingly looked much in that direction. I do know there are a lot of ties to cohomology and homology with discrete Morse functions. I personally, to be honest, I haven't looked into it. A good source to look at if you're really interested in looking at more is probably at least the first best source you can look into is Forman's, what is it? User's Guide to Discrete Morse Theory. User's Guide to Discrete Morse Theory.
Okay.
Yeah, so sorry for not having a more concrete answer on that one. But yeah, no, that would be interesting to hear more about that. I personally haven't read this entire guide, but yes, I will. Okay, but yeah, I'm gonna write out this word though for obvious reasons. But yeah.
Hello, I have one question.
Sure.
This is where you talk about the Forman's proof that could you please go back to the slide where you showed where you wrote this thing about the Forman's result in 1999, I guess. Yeah.
What was the theorem statement again, or the
Forman's
wait?
theorem that he proved. Yeah. Yes.
Oh, this.
Yeah. So I was wondering if we can if the converse of this result is true. Just wondering.
I believe in Forman only showed one direction. So let's see. So
because I can see that I can see if for the manifold of dimension 4 this is mysterious because we don't know whether manifold of dimension 4 admits CW complex structure or not. But other than that, can we Yeah,
I don't know about the backwards direction. I know in Forman's work he only proved this direction, that going from a smooth manifold, you can construct a discrete Morse function on its triangulation that gives you back the same stuff. I'm not sure how one would phrase the backwards direction or things like, or what exactly you have in mind, but I haven't seen anything that goes the backwards direction. And
oh, okay. And I was wondering if there is a connection between Morse pair and Morse-Mel function.
Morse-Mel?
Yes.
Wait, what's the first thing?
Morse-Mel function and Morse pair. Is there any connection between them?
Morse theory? Was the second one?
Oh, I'm sorry. Maybe I think you didn't use this terminology in this talk, Morse-Mel.
I know what Morse-Mel is, at least in the smooth case. I think there's something in the discrete case as well that mimics it. I haven't read up on it, but I do know it's something that Forman worked on, a discrete version of that. But that's the most I can say. I've only studied the smooth Morse theory one.
Okay. I just found something interesting. Can I share my screen if I may?
Oh, sure. Here.
There's an interesting result I found.
Where is it? There.
Okay, Chandon, you should be able to share now.
Oh, okay. Let me try and do that.
Thank you.
Can you guys see my screen?
Yes.
Yeah. So here, this result, I guess. So this sort of it basically says that there are a finite number of gradient flow lines from one point to another point, and this is in some sense counting. I think this is what you did for a simplicial complex, I guess.
Yeah, that almost resembles it. Yeah.
Yeah. So that's why I was wondering if there is like this function which the definition is slightly different. So I was wondering if this is the same analog of what you did for discrete case.
I'm not sure. I'll have to think more about that.
Yeah. I just found it interesting. And also there is a result in a smooth Morse theory that gradient lines flow the gradient line decreases along. Sorry, the gradient flow decreases along. Sorry. The Morse function decreases along gradient flow lines.
Yes.
Yeah, and in one of your examples, I feel like the gradient lines that you defined for discrete cases, they also decreases, I guess. I mean, I just quickly observed. Is that true in discrete Morse theory?
Wait, what's true?
That the gradient line decreases. So sorry, the discrete Morse function decreases along gradient lines.
Yes, that is indeed true, and that's how it was constructed in that one proof.
Okay, that's good. Yeah, that's all I have to ask. Yeah, thank you.
I also had one question. I was wondering so kind of related to the Forman result, do discrete proofs, are they sometimes more efficient? Well, it's certainly more efficient if you prove it for the discrete case than you know it for discrete and correspondingly smooth. But are the proofs sometimes easier in that case?
I've found that the proofs are very very straightforward in discrete Morse theory case. In smooth case, you have to deal with analytic things and so on. Yeah, so that is kind of an interesting thing to mention, that like just doing stuff in the discrete case, then just considering manifolds afterwards and trying to imply everything that way. But yeah, I found the discrete proofs to be fairly straightforward, but I've never seen someone prove something in discrete case in order to say something about a manifold afterwards.
Any other questions? Well, if not, I'd like to thank Andrew again on behalf of everyone. So thank you.